Anyway, it's great to be here, and I appreciate you all coming out. And can I dim the lights at all, ma'am? Okay. So what I want to talk about today is science and engineering and how it relates to communities. And I'm going to talk about it at a global scale and at a local scale, basically. And as many of you know, science and engineering, we've almost done too good of a job in some ways because we're kind of detached from our communities. They don't know what we're actually doing. I was talking with Larry at the underground mine today, which is really, really neat to go through. But he was talking about mining and how people, my students tell me, Ken, I'm completely green, I don't hurt the earth, and they have like 4 different, cell phones and all these things that you use metals for, and they're plugging them in and recharging them. We can't go on a field trip unless they can recharge their phones. And so we, it's the same way with farmers. Everyone used to know a farmer, and now we're very efficient at it. And so we've kind of really become detached, basically. We become too specialized. So I just want to talk about the impacts of, from a global perspective, the role of science and engineering as it relates to large earthquakes. And then I'm going to talk about what some of our students are doing to bring science back into native communities. So just to give you some background on who I am, as Bev said, I like to study tectonics. So I like this is one of our camps up in the St. Elias, but you can see these are sedimentary rocks, so they're stratified rocks, and these are medium-grade metamorphic rocks. And so how do you get those kinds of situations? How do you get parts from the middle crust, sedimentary rocks that are recording those processes, or things that interest me? Here the students and I are working on a project near Mount McKinley, is right back in here, but this is a Jurassic sedimentary basin with marine fossils. How do you build the biggest mountain range on Earth? These are the kinds of questions I was interested in, and this kind of gives you a feel for a beautiful fold here. There's a student with a blue shirt. This is his thesis area here. But as I was working on these problems, I always wondered, how do you reconnect this back to communities? And so what I started to do was to work with civil engineers, mainly structural engineers that work on buildings, and geotechnical engineers. And we started working on earthquakes around the world. So this is a picture from an earthquake in western Turkey. These are apartment complexes, buildings that have been totally destroyed, as you can see. A conservative estimate, it's sometimes hard to get the actual numbers, about 30 to 40,000 people died in this earthquake. This is where people were living right after the earthquake. And Turkey is located right here. And what's going on is that you have this Arabian plate that's colliding with this Eurasian plate. And so the Anatolian plate is getting pushed out this way about 2.5 centimeters per year. Basically, this western part kind of looks like the Basin and Range for you guys that have been here. It's collapsing out into the Mediterranean. And there's 2 big fault systems, one down here and this North Anatolian fault system through here. Istanbul would be right here. The next slide is from this area, from some of my Turkish colleagues. And so here's the Bosphorus, connects the Black Sea with the Mediterranean. So this is the most populated part of Turkey. This kind of shows the epicenter of where the earthquake that we worked on. You can see the seismicity along the fault system. One of the areas that we're really worried about in the world right now is Istanbul. 14 million people. That segment of the fault is locked. So what I mean by that is that this is from some of my French colleagues. And what I want you to look at here at the plan view, so here's Istanbul. We had earthquakes, you can see, I can't say it that well, 1939, 1942, 43, 57, 57. Here's the earthquakes that we worked on in 1999. This is one of the places in the world where this idea of earthquake triggering was first developed, that you have one earthquake along a fault segment, it loads up the next. You have displacement there, it loads up the next. It's like a big car wreck on a freeway. And you can see that there's this big seismic gap, or what we call a locked fault, right where Istanbul is. So this is one of this and the Cascadia region are areas that we're really concerned about. So after a big earthquake, I'll jump in the airplane with a bunch of civil engineers, and we'll take off and we'll start documenting things. So they drop me off, and my students and I are mapping the rupture along the fault after an earthquake. So you can see where the ground's been displaced. In this area, this side has moved up. You can see a down building over there. So I'm moving along the fault zone, trying to understand how the ground moves so engineers can start to use this information. Here you can see where the fault rupture, this side over here has moved down. And these things are very complicated. This is kind of a common situation. I'm moving along, and I try to talk with people as I'm going to find out what happened. So I was talking with this guy right here, and I said, what happened during the earthquake? And of course, I don't speak Turkish, so it's pretty hilarious, some of the things that in our conversations. But he said, oh, so you're sleeping. And it happened at 3 in the morning. And then he goes, oh, the building starts shaking. And then he goes, so you're running out of there. And he goes, boom. And I said, oh. And then the fault rupture runs right along the side of his house here. And you can see what happened to his steps. This is a right lateral fault. So this used to be right there, okay? And all this happens in 38 seconds. So by the time he woke up, ran out, his steps had already moved, okay, about 70 centimeters. So since I don't live there, I like these for marker beds because it's a nice marker bed that I can start to say how much that fault has moved there. And, I worked my way along the fault system. So here, this was a fence that was just being put up, and you can see that at one time it was right here. You can see the fault rupture coming down. So there's about 1.5 meters of displacement there. So I can start to record how much the ground was moving. You can see the fault rupture. It splits trees as it's moving along. And then I can start to give the engineers a map of how the ground was moving. And the engineers are interested because they're looking at the building, especially the structural engineers. So some buildings collapse completely. Often what happens in these big earthquake areas is that the first and second floors get sheared out, okay, because the whole building is swaying. And then you start to have shearing, basically. So these are very dangerous places to live. And then other buildings make it through. And so this is where this built environment, of course, is where a lot of people get hurt or killed. And so you can see a couple beds here. You can see a heating radiator. So when these things collapse, you don't have much time. So the built environment is really important. They want to know what kind of stresses the building was undergoing along that part of the fault system. Now in Turkey, one of the things that the engineers pointed out to me is that there was a lot of bad construction. This led to a lot of political unrest in that area. So here we're looking at a column for a building, and you can, my scale is down here, 15 centimeters, but you see all the rust basically on the steel here. So that usually means that there's some kind of a bad cement job, and there's a lot. They built these buildings very quickly. They were trying to make this an industrial society. These things that are hooked here, this is part of the building code in the US, but they're supposed to take those and tie those in to the vertical pieces of steel or rebar. And so what that does is give you this lateral continuity as that building's moving back and forth. But in this case, again, they were putting them up in a hurry. They didn't do it. So we have that kind of information, but we also want to know buildings that are well built. So here's a column that, again, you can see it was destroyed. So we can take this information back to Purdue. This is the Bowen laboratory here. There's a couple computers there to give you a feel for scale. And what you're seeing is that they've made a large column here, and they make different types to see how they hold up under different stresses, okay? And then they can deform these basically and say, and so this has been rotated, so that bar there is that bar there. But they can start to see, when does this fail? If you add a lateral horizontal shear to a vertical shear. So we can start to tell these communities, this might be the best way to rebuild these buildings. And you can do it with bridge columns. You can do it with a number of things. They'll try different types of walls, so this is concrete shear walls with lap splices. So all this information allows us to help these communities understand how to rebuild, and it gives basically the entire globe. The ironic thing is that, and part of the reason people in Turkey were so unhappy, most of their older houses are wooden houses, as you can see here, and they held up fine. I mean, obviously there's some damage. And that's one thing I'll point out throughout this talk is that there's a lot of information that these communities already have when we talk about Native American communities as well, that it's not really being utilized. So Turkey, again, they went from the 1960s to 1970s from a very agricultural society to an industrial society. They built all these buildings, and basically people had no say. They didn't understand what was going on with the buildings. Let's compare this to Taiwan. Taiwan is this island right there. It's part of the Luzon volcanic arc. This volcanic arc is being transported this way, and eventually all this material will accrete onto the continental margin of China through here, southeastern China. So this is one way that we grow continents. That's why I first started studying Taiwan. This is a close-up of that same area. So Taiwan had 21 million people in it. Okay, this is uncommon for Singapore and islands like that. So it's about the size of New Jersey, guys. New Jersey is our most densely populated state. It has 8 million people in it, and most of it's pretty flat. Taiwan, the backbone of it here, these are 4,000-meter peaks here. So most people live out here on what we call the foreland side, or up here in Taipei. Okay, so you have this high concentration of people. All these peaks have formed the last 3 to 4 million years because of this collisional event. And so you have some just amazing earthquakes. So this was a flat-lying river the first time I worked in Taiwan. I came back right after a big earthquake in 1999. This is the fault rupture right through here. You can see what it did to this bridge. Over 220 bridges were damaged during this earthquake. And so here I'm working with my colleagues from the Northern Taiwan University, but this is a track at a school, and basically you can see this hanging wall side has been moved up, and we're mapping out the trace of this fault so we can know where we knew there was a fault here, we didn't know that it was active. This is the area where we had the most displacement on the fault, so you can see my colleague there, Yu Gao Chen. But this surface was equivalent to this surface, so there's about 10 meters of displacement here. Okay. So you can see, very dangerous situation. But what's remarkable, this was a 7.6 magnitude earthquake. What I showed you in Turkey was a 7.4. Only about 2,400 people died in this earthquake because Taiwan is pretty well engineered. Most of the people that died were in situations like this. So you can see the fault rupture coming through this rice field here. So this side has moved up. And it was mainly houses that were located right adjacent to the hanging wall. So the side that moves up, if you're not a geologist. And I asked the people in here what happened, and this happened at about 2 in the morning, and they said they were in bed, and they felt themselves being thrown up in the air, okay? And then your bed is usually next to a wall, and they felt the wall hit them as they were pushed forward. And you can see that with these houses as well. They've all been tilted up. Because they're in the hanging wall of this fault, you're starting to fold this before it breaks. This is one of the reasons we get folds in hanging walls, and then it breaks. And so the people were feeling these geological processes. So what we can do in Taiwan is we map out these faults, and this kind of shows this is that same area, but here's street level here, and this is off the map, and the street level is now down through here. But you can see basically this has all been bent down like that. And so we map out the fault rupture. So this was a golf course. All this was flat at one time. But in Taiwan, with 21 million people, you can't say you can't build here. But what you can say is don't put critical infrastructure here. Gas plants, hospitals, schools. Okay. Okay, so we're going to leave Taiwan. This was after that earthquake, I worked over there for 2 months, and so I was starting to miss America. And so this is one of my favorite places because they had a basketball rack at this temple, and I could play with the local kids. And but really an interesting place culturally. So Taiwan did a fairly good job. We're still learning where the faults are. Faults are hard to map through a jungle in some places. Southern Taiwan is very tropical. Let's go to a place where the system basically failed the people. Let's go to Haiti. So this is the presidential palace in Haiti after the 2010 earthquake. I'd been in there a year before. We were setting up GPS instruments. And so basically, as I'll show you, every government building collapsed. About the numbers, the Haitians say that over 250,000 people died in this earthquake. There's been other studies that have said about 159,000. University of Michigan did a study on it. But basically, the country was devastated. Schools were destroyed. Churches were destroyed. As you might know, Haiti is the poorest country in the Western Hemisphere, and so they're really never going to recover from this in any strong way. But what was really remarkable was that there was no emergency plan. So here you live, and I'll show you why this is such an active fault zone. The U.S. took over the airport to get supplies in. There was no emergency program there to how to handle the airport if you needed to get supplies, water in. Relief agencies were ready to come, but they couldn't even get into the airports, basically. All the hospitals in Port-au-Prince were destroyed. Some of the main roads coming in, it took 8 days to clear them out. And so there was no plan at all. So these people were totally unprepared for this disaster. And the sad thing is that there had been 3 studies, and one of them was ours, that this was a locked part of the fault zone, and that this was going to happen. And we can't say tomorrow or 10 years from now, but this energy was going to be released at some point. And as you might remember, after this earthquake, the area was hit by a typhoon. It was just incredibly sad. One of the geologists, actually a geophysicist that I worked with, became the UN kind of scientific ambassador for Haiti, and we still haven't made a lot of progress. But again, the people are still suffering, basically. And why Haiti is so dangerous is that it's located on this plate boundary between the Caribbean plate and the North American plate here. This is a particularly thick part of the North American plate called the Caribbean platform, the Caribbean platform. And there's faults all along these boundaries, as you can see here. This is the subduction zone here, and this Caribbean plate is moving about 2 centimeters that year. So the reason that you have all these islands down here is because of the tectonics. And we have a long history of earthquakes in this area because, as you probably know, Haiti was colonized by the French, the Dominican Republic was colonized by the Spanish. So 1751, Port-au-Prince was destroyed. You can see all these big earthquakes along different parts of the fault system. The first time I went to Haiti, if you study tectonics and we come into Port-au-Prince, this area is called the cul-de-sac here. So you have big mountains here, and this big valley just sitting in the middle. You think, oh man, this is just, because classic signs of a big fault system. You see this, that's what happened in Turkey as well. Most of the people live along the Anatolian fault system because you have little pull-apart basins where there's lakes. This is where you can farm. Same way with the San Andreas. Okay, so most of those earthquakes are what we'd call kind of upper plate earthquakes. I want to talk about something now with earthquakes, and it's really with tsunamis and subduction-related earthquakes. So these earthquakes have longer recurrence intervals, so we don't know them as well. And there became a lot of money available to look at tsunami-generated earthquakes, and part of this was the 2004 Sumatra earthquake, as you might remember. 230,000 people were killed by the tsunami and the earthquake together. The Indian Ocean has no early warning system. Okay, so people that could have had hours of notification weren't even ready for this. Then we had a big earthquake in 2011, as you know, in Japan, and I want to talk a little bit about what happened there. And Japan is a very complicated tectonic area, but the earthquake that we're going to be talking about, here it's listed at 8.9. We've remodified that to about a 9.0, but March 11th here. And you can see that I've plotted, there's lots of big earthquakes within Japan, and they were fairly well prepared, but there were some things that we learned that taught us quite a bit. Japan is situated between four different tectonic plates here, shown here in plan view. If you want to get people arguing, get a couple geologists talking about the tectonics of Japan, because it's so complicated and we're still learning so much about it. But you can see, so here's the Japanese islands here, so that is that. It crosses several different plates. And I don't have the QuickTime. I'm a Mac guy. I'm sorry about that. And so on this computer, I can't run it. But I have a lot of news coverage. But I have some good photos of actually what happened. But when you have a tsunami, of course, these things can go 10 kilometers inboard. And you can start to see where it's starting to cascade over this irrigation ditch here. And Japan is one of the best engineered countries in the world, but they weren't ready for this, and I'll let you know why in a minute. But these are some before and after photographs, so communities that were impacted by it. So this is the town before, and you can see every house was basically destroyed. Another kind of before and after photograph. And what's left behind is just, I mean, it's almost hard for us to fathom as human beings, this much force. This was near a railroad depot. Japan thought they were ready for these earthquakes, so they had tsunami walls. They had prepared for about a 5-meter high tsunami, so about 15 to 20 feet high. And you can see basically what happened. You can see cars coming over. It saved them some time, and we were lucky in Japan in that, 15,000 people perished. There's about 2,000 people that you lose people with these big tsunamis. You don't know what happened. But they had a little bit of warning, so there was a few foreshocks, so people kind of knew. There's lots of geophysical instruments here. So like in Tokyo, about a minute before the big earthquake, they were told, take shelter, we're getting a lot of seismicity off of this zone. If you just have 15, 30 seconds, you can save hundreds of thousands of lives, basically. They even had these evacuation platforms where people were supposed to go if there was a tsunami. And you can see, they were prepared for this 15 to 20 feet high, and this is the level of that tsunami. So even if you took protection, and you could see it from, just what happened. You have cars on top of 3-story buildings. This photograph, so you have a large house here with another house that came from somewhere, presumably over here, sitting on top of it. And what's amazing about Japan is that all over Japan, there's what they call these tsunami stones. And basically what they're saying is that the water came up to here. Okay, so they're telling, some of them were up to 600 years old. So they're telling future generations, don't build below this point. Okay, but Japan is an industrial nation, great shipping nation, shipping cars out to us and all over Europe. And so they thought they were prepared, and I think, they did a good job for what they thought they had. But again, it just tells you there's so much more that we have to understand about these subduction-related earthquakes. This is what we're worried about with Cascadia as well. So towns like Seattle and Tacoma, all along that coastline, all along the Alaskan coastline, when you talk with native people, and they'll say, we don't build houses in this area. And when the Europeans first arrived, they were like, well, why? It's so beautiful. And they'll say, we have a story there about waves crashing on the village. And people would basically laugh at them. And they built all these big homes. Now we're going back into areas like the Puget Sound, and we're taking cores, and what we find are these layers of dead trees with a layer of sand above it. So these are all tsunami deposits, because when that salt water comes in, it kills all the trees, leaves this coarser material, and so you can find these throughout. And again, it looks like they have a recurrence interval in Cascadia of about 500 to 600 years. So Europeans haven't lived on this continent long enough to actually have this kind of information. So most of you guys have some earth science background, but I think you can start to see from what we've talked about with earthquakes that most of these occur along plate boundaries. There are some exceptions. I've kind of showed you different types of fault boundaries. So I showed you in Turkey where we have a strike slip where things are moving horizontally. I showed you in Taiwan where we had a thrust fault. So we have to understand the dynamics of these systems. And, you know, I showed you up here in Turkey, in this area, we looked at Taiwan, we looked at Japan, but you can start to see the distribution of earthquakes, basically. So we're never going to get away from big earthquakes, but we have to use as much science and educate the communities. One of the things that we're doing in the U.S. is we're running a really large geophysical experiment right now called EarthScope, and some of you might be involved in this, but what we've done is we started on the West Coast. I'll show you another slide, and we've moved all the way across the East Coast. This is where we're at right now. And all these dots basically are where we have seismometers, GPS stations to start to understand kind of the crustal structure. There's different parts of EarthScope, and one part is drilling down into the San Andreas Fault Zone to start to understand kind of the fracture mechanics of these zones. And some of the things that are pertinent to this talk, these are the goals of EarthScope: active deformation of the continent, earthquakes, faults, tectonics. Like I said, this is where we're at right now. So you can see that 2013, the green right here. And why I've been involved with this program is that we're moving to Alaska. That's what we're doing this year. We have a few stations set up in Alaska. So as we finish up with these seismometers, we'll be actually working in Alaska. We had argued to NSF that Alaska was the first place that you should go because it has big subduction zones, big earthquakes, the 1964 Anchorage earthquake, but California has a lot more leverage than Alaska. But again, in the U.S., we're trying to do something about these phenomena. As you can see that if communities aren't prepared, this kind of devastation is going to keep occurring. We're going to have more and more people on the planet. You guys know the population is supposedly doubling. So we need to understand where people are living, how to prepare these tsunami walls, how to let people, early warning systems. So what I want to do now is move more to science and local native communities. Okay, so go from a global scale to a more local scale. And as Bev said, a lot of us in this room are working with the Sloan Foundation to get more Native Americans into graduate programs. And often with Native communities, they don't see the role of science in their lives. And so that's one of the things all of us that are working with Sloan is trying to do. And mostly we're trying to do it through the students. And that's what I want to talk about. Okay. So this is a project that we're doing up in the Red Lake area. These are two Ojibwe students. This is Kevin Gibson. Some of you guys know him. This is a professor from Bemidji State. But I can go up to Red Lake or Leech Lake and say, okay, Purdue has one of the top 5 structural biology programs in the world, and these kids are just falling asleep faster than you could count, okay? Because it doesn't mean anything to them. But if I say, if you come to Purdue to get a master's degree, you could study the DNA of the rice, the wild rice, in Red Lake or in Leech Lake. All of a sudden they're interested because that's part of their culture. Some of you might know, some of you may be Ojibwe people. Basically, they're the people of the wild rice. They're Algonquin-speaking people, so they're related actually to my tribe, the Delawares, and they left the East Coast. Part of what they were told by their elders was that when we get to a place where there's food on the water, that's where we're supposed to be. And so when they got to this area of Minnesota, Wisconsin, they had the wild rice on the water. That's where they were supposed to be, and they were supposed to take care of that rice. So here we're making a connection with science, but as it relates to a cultural context. And so that's what we've been trying to do, and I want to give you a feel for what some of the, what some of the Purdue students are working on. But I've been around the country talking on different tribal lands, and some of the things that come up with Native American communities, really from Alaska all the way down to Hopi, are things like global climate change. So when I talk with elders out like on the Kuskokwim River and out in the Yukon River, and they'll say, I'll be in this little village, and they'll say, well, when we were little, we used to watch where the caribou would come between those two hills right there, and that's when we knew it was time to start hunting the caribou, that they were moving back. But the bushline has moved up so high as the climate has changed that they can't use that area anymore. So they're relocating where they're hunting. The Eskimo people, their villages, as you know, you've heard about these villages that they have to move 2 or 3 times basically as the permafrost is starting to melt. All these issues about drinking water, really important for the tribes in the Southwest. For the tribes in the Midwest, forests, controlling the forest, using it for timber, but also maintaining it, like Menominee, those folks, really big issues. Energy resources, actually here in Montana, the Crow Reservation, as you know, there's a lot of coal on it. And there's been a lot of people that have wanted to mine that coal, and I talked with Russell Stansoverbull from that area, and it's a big issue with the Crow people. These are big issues that are having impact on these communities. Nuclear waste, as you guys know, Yucca Mountain is not going to happen, at least for a while. Harry Reid is in charge of the Senate, so it's not going to move out of there. And so we have all this radioactive waste that's being stored on these temporary facilities that some people feel are terrorist, targets. And so a lot of tribes have been approached about storing nuclear waste in their area. But all of these problems are problems that, the scientific community has a responsibility to let communities know and to find students that can work on these problems. And so some of the things that we try to do at Purdue, so this is up at Red Lake, but working on a forestry project, we try to find professors that will actually go out in the field and work with the communities, basically. So this is Kerry Ravenbull. He's a botanist, and he's working, with this student. She's a non-traditional student, but they're doing forestry plots, trying to restore different parts of the forest. There's all kinds of questions about what it actually looked like before. But part of what I talk with when I talk about these types of issues with Native communities is who's going to make the decisions that are going to impact Native communities, basically. For a lot of us, we've already felt like we've been pushed onto marginal lands to start with, so we're even more vulnerable to things like climate change. And what the Sloan program and what Purdue, we've tried to say, what we need are Native scientists, teachers, engineers, politicians that are helping make scientific decisions for their own communities, and that's kind of the goal. Just to give you a feel for what these students are working on, so this is one of our first Sloan students. This is Leanna Begay. She's from Tuba City, Arizona, and she was really, Navajo people haven't grown up with a lot of fish, so it was kind of cool to have her in this class. And we get in, I was telling Martin back there yesterday, with the Navajo students, we have a couple students from Hopi and Akba. We always do a canoe trip in the fall, and I'll be helping the students get into the canoes, and I'm trying to tell them, okay, so you can't move, whatever, and they'll be out, just about a foot, and they're over. And so we always talk about capsizing. But what Leanna wanted to work on was sand dune migration on the Navajo reservation. And as I mentioned, she's from Tuba City. This is a road that her grandparents live on. And with the regional drought out there, the water table has dropped. Okay, and what that does, it frees up more sand, basically, to move around. And so this is an active sand dune, basically. And you can see that it's covering up the roads. You can see where someone's tried to drive over them. And about a third of the Navajo reservation are sand dunes. Most of them are stabilized. But talking with her uncles, what they've told me is that there's also that when the sand dunes start to migrate, that people start to be concerned, basically. This is an area that has regional droughts, as you know. And so this was near her grandparents' house, a house that was just basically covered by a sand dune in a period of a couple of years. And so what she worked on was using native plants to try to stabilize these dunes. And that's what she did her thesis on, what plants work better. She had plots on different dunes. She had to learn basically the physics of sand dunes, and that's what she did in our department, but she was also working with botanists over in biology. And now she's back in Navajo working on this same topic. But again, it kind of gets to that point that I'm making about having Native students work with their communities to solve scientific problems. We also have Hawaiian students. This is Marie here. This is her grandmother. I use this for my recruiting slide. I always tell students, this is what Indiana looks like. And the smart ones never believe it, of course. And but she, obviously she's Native Hawaiian, and their diet has changed considerably, as you guys might imagine. And they're having all kinds of problems, like a lot of the tribes in the lower 48 with diabetes. And so the project that she ended up working with was with 3 tribes out in the Pacific Northwest, these 3 tribes right through here. All the red shows native land in the state of Washington. But these were people that were having big problems with diabetes. Traditionally, they'd ate razor clams, seafood, and their diet has changed so much since the Europeans have came that they're having all these health issues. So she was in nutrition, and that's what basically she worked on, trying to come up with better patterns for eating and making people aware of some of their choices. Daryl Reno is from Acoma Pueblo out in New Mexico. He works with my research group. And so this is Acoma Pueblo here. It's out in west central New Mexico. This is the oldest continually lived in town in North America, okay? Now, them and the Hopi argue about that apparently, but it's pretty darn old, thousands of years, okay? And his grandmother's house, I think it's this one right here. So this is the framework that this student grew up in, okay? And so we look at that as geologists and geophysicists and just say, man, you're just surrounded by geology. This is the Colorado Plateau, okay? So when I was trying to convince him to go do a master's at Purdue, and he said, well, I don't know how I could use geology, basically, back home. And I'm in his grandmother's house, and for you guys that are sedimentary geologists, and they cut the rock out of the Dakota sandstone here, and there's like foresets and all kinds of sedimentary structures. So it's like a dream for sedimentary geologists, because there's all these said structures in their house. And then you look at, so they're just tied in with the stratigraphy of the Colorado Plateau. So what Daryl's doing for his master's thesis is he's doing what sedimentary and structural geologists would consider kind of cutting edge things, looking at uranium lead dating of detrital zircons and things like that. But what he's using it for is to develop a curriculum for the reservation schools in Acoma. And so tying in the stratigraphy with the way that a person from Acoma would look at it. So most Western geologists would say, okay, so here's the Morrison Formation, here's the Dakota Formation. But to an Acoma student like Daryl, he said, okay, so this is where we get our sandstone for the houses. This is where our farming lands are. This is where our natural cisterns are. So they tie in how they live at Acoma with the stratigraphy of the Colorado Plateau. On the verse, this is from a poster that he gave at Geological Society of America, and you can see the title, Cultural and Geologic Connections at Acoma Pueblo, New Mexico. On the one that he gave to the tribe, he actually has where they actually, certain clays, these are great potters, basically. His parents are potters. This is his aunt right here. So again, it's a non-traditional kind of thesis in that we always have to ask the tribes, what information do you want in this thesis that's going to go into Purdue and into our library? And they said, we don't want the information about the clays in there, okay, because that's important to us. But you can start to see, if you look at his conclusions here, they're hard to see, but the geologic framework of Acoma Pueblo is interwoven with the cultural and I can't read that from here. I can read it on the computer. So one of his conclusions, the geologic framework at Acoma Pueblo is interwoven with the culture and lives of the people living there. There is a potential to create land-based curricula that reflect both native and Western perspectives of science, okay? So this is what I mean about doing science that's important to the communities, that respects the way that they look at the Earth, but also the way that Western geologists and geophysicists would look at the Earth. We just have a couple more here. This is Tanya, and she is from northern Wisconsin. She's an Ojibwe. This is a professor from Purdue that's working with her. And what she wanted to work on was reintroducing the pine marten to the woods of northern Wisconsin. So the pine martens are one of the clan animals for the Ojibwe. Clan animals, again, these are Algonquin people, so I know a little more about them, but they're very much like the Delawares, my tribe, in that clan animals are really important. If the clan animals are doing well, the people are doing well, okay? And so because northern Wisconsin's been cut several times by timber, all the habitat's gone, basically. So on their tribal lands, what they're trying to, they took pine martens from Minnesota, they brought them into tribal lands in Wisconsin, and so what she's doing is trying to understand how they're doing, what parts of the forest are the best for them. This is one of her assistants. She got a big guy to do a lot of it. So I said, that's your assistant? Man, he's huge. And then she goes up in the wintertime and they're tracking where these animals are, how many deadfalls are in the area. But again, something that's kind of cutting edge wildlife biology, but also this important cultural connection. I think the last one is Mike King here. So he's from Navajo, and he worked in our department on atmospheric science, looking at air quality. So this is up in Page, Arizona, and as you probably know, there's 4 big power plants basically on Navajo land or adjacent to Navajo land. And they can bring coal right from the local nearby rocks. They're making electricity that goes mainly to Las Vegas, LA. It's kind of ironic that there's still parts of the Navajo reservation where there's no electricity. Okay, people go and haul their water, as you guys probably know. But the Navajo people are very interested in what's going on with these emissions. How does it affect our sheep, our people? So what he did is he set up a monitoring program on that part of the Navajo reservation, and now he's working with the Southern Utes to set up a program. There's this possibility, you know, the EPA says that tribes now can take control of their own monitoring, and so there's this need for a lot of atmospheric scientists that come from native communities, okay? And then we've also been trying to work with students at earlier ages to let them know what's going on. So this is on the Paiute reservation. I'm working with a couple students and we're mapping out a fault. And so the Paiute are the people of the springs. That's what the local people called them because they were located along these springs on the Colorado Plateau. You look at it as a geologist and all their springs are on these north-south lines because they're right along the big normal faults, like the hurricane faults that you guys might have heard about that are geologists. And what they do is that they bring down the Navajo sandstone, which is the big aquifer out there. If I'm south, everything's kind of tilted up towards Utah. They bring that down against usually the Triassic Chin-Lee Formation, the petrified forest member, which is this red shale. You guys have probably seen that as you've been traveling. And so the water comes down from Utah, from snow, comes down through the subsurface and works its way up through the fault system. And so we go out and we're mapping with these students the different rock types. And it's a great, for me as a geologist, because you have white rocks against red rocks. And these students, they know where the springs are. We go for picnics up there, you know. And so we're mapping the fault. But again, it's a way to bring it in the culture. The Paiutes have a lot of different things that they do with the springs to maintain the springs. We were with an elder. We try to bring out elders as we're doing these projects. And so we're mapping along the fault zone, and I'm teaching them these students about things that you guys have gone to field camp or been in structural geology, slick lines in faults and which way the faults are moving. And we were trying to locate ourselves on the map, and I asked the elder, I said, what do you guys call that mountain that's right in the middle of, you know, what I would call a fault zone? And he goes, we call that Thunder in the Mountain. And I was like, really? Because as a, person that works on earthquakes and fault zones, but in their, in their culture, at one time there was thunder in that mountain. And so I'm assuming it might have been an earthquake, okay? But how cool that we can use GPS, because these are still active structures, as you guys know. So bringing in this indigenous knowledge that's been acquired over thousands of years with the latest technology that we use to understand how the Earth performs. So again, I think for the questions that we need to answer, we need to connect with local communities. And one way to do it, I think the best way that I know right now, is to have their students work on it, go back to chapter houses, go back to tribal centers and say, this is what we found, this is the situation. Often they just have a pretty bad impression of scientists, basically. And because of a long history of boarding schools, people using resources. But this is a way to give these tribes tools, and they're ready. You know, one of the things the Native students here can tell you is that, you know, with tribal colleges now, with more students getting undergraduate degrees from Native communities, it's kind of an exciting time for Native communities in that they're ready for graduate school. Not every student, but it's really time that Native communities can become the expert witnesses, can look at the data, can analyze what's important to their communities. So hopefully what I tried to show you in this talk is this global perspective, people making decisions about how they want to handle earthquakes or not handle earthquakes. You know, in situations where people weren't prepared, 230,000 people died in the Sumatra earthquake, Haiti. Situations where they're prepared, there's still going to be deaths, like I was telling you with the 2011 Japan earthquake, with what's going on in Taiwan. We still have a lot to learn, but these decisions have big impacts on communities. And I hope I gave you a feel for how the role of science in local communities. I often tell a lot of our Native students that, to me, a lot of the issues on Native lands are issues that our entire nation has. Like I said, climate change, resources. You can't take out environmental restoration without an energy component. And I think they could actually be microcosms of how we could solve some of the bigger nation problems. Because you're dealing with a smaller community, if you could really get wind energy to be a main source of energy on the Navajo reservation where people are trying that could be kind of a prototype that we could use. But somehow we have to get science back to communities. And again, I think a lot of us, you get a PhD and then you get a postdoc, and we're not connected with the communities anymore. And we have to somehow get that back if we're going to, you know, make an impact on these communities. So I'll stop there. I had a really nice time at your university. For the students that are in here, they're getting a great education. I was in an underground mine today, seeing how they do things, and but it's really nice to be here, and I, you know, appreciate the opportunity. So thanks a lot. Mm-hmm. Absolutely. Uh-huh. Sir? Oh, absolutely. Uh-huh. Mm-hmm. Mm-hmm. Yeah. And so basically, as I said, these are subduction-related earthquakes. So what happens when you have a big subduction-related earthquake? This upper plate, this downgoing plate bends, okay? So in the case of Sumatra, it rose about 8 meters over about 175-kilometer length. So you can imagine, you guys, when you were kids in the bathtub, right? And you're like pushing your hands on the water, and the water would go up here. So that's what happens. But what we do, can I write on this board, Bev? Well, what's interesting and what we don't understand very well, so this is the downgoing plate. Here's our upper plate here, is that, so what I'm talking about is you have a big earthquake down in here in the seismogenic zone. This plate buckles up, pushes seawater forward. But we also know that there's faults, which we call out-of-sequence faults. So there's also smaller faults on that plate as it's bending and going down. And they often are a little bit steeper. So what happens is you can get some of the tsunamis come to these villages really early. And so we were really surprised at some of these, because you have to understand what's going on also with the local structures. It's just not that deeper plate sliding down during a big earthquake. And so you can have these more local faults, and if they're a high angle and there's a lot of displacement, again, you can see that you can get tsunamis even moving quicker towards these communities. But the other place that we get tsunamis are big landslides associated with the earthquakes. And so if you have a big landslide that comes down into the ocean, again, it's like moving your hand through your bathtub again. You can have tsunamis as well. And we know these are important, but it takes these big catastrophic events like Sumatra and like Japan for us to really get back to them. And that's, again, what we're worried about with Cascadia. So, yeah, if I wasn't clear on that, there's pretty much a connection between the two. Good question. Absolutely. Any other points? Sandy? I'm not sure what that is, but usually there's several out in front of it. And then, like I said, it went all the way across the Indian Ocean in the case of the 2004 Sumatra earthquake. And what's interesting with radar, and this is something that's pretty encouraging, is that you could actually see the sea level rise about 2 to 4 meters. So we think that might be a way to get some early warning detection, because it's hard to get these detected. So they're really long wavelength features, and but they usually come in there's cycles of them, basically, because the earthquake, the fault's breaking, and then it breaks again, and then it breaks again. And so, but again, as you might remember from the Sumatra earthquake, water moved all the way out, and people were actually going out there like, hey, we can go out there and collect fish, and there are things that we can teach people, right? I mean, that's getting knowledge, that's preventable, and that's what was so sad about that earthquake, I think, to people that work on earthquakes. Again, no early warning system, so people dying 2 hours later, there's just no need for that, basically. You had a question, Miss? Oh,
It seems like every other day you see a newspaper connection or presumed connection between hydraulic fracking,
uh-huh,
drainage fault,
right, uh-huh,
earthquakes, and the debris and the lead, which is resulting
mm,
I'm sure that's late goes on. Because I don't see the science in that.
right,
I see correlations that
right.
find very helpful.
No, it's a really important question. I was giving a talk at University of Oklahoma, and that's one of the areas where they're getting a lot of earthquakes, and there's a lot of fracking. I think, from my perspective, what's going on, it's not the fracking process itself. We've been fracking wells for 100 years, vertical wells, as you might know. We drill down, and then we'd frack out into the reservoirs. But now what we're doing is, with these non-conventional wells, going down and then going, laterally, sometimes 2 miles, and then we're fracking those under high pressure. But what happens is that you're introducing, it takes a lot of water, basically. And I think that water might be the underlying cause. And as you know, if you lubricate something, basically, so if you have an old fault zone and it's under hydrostatic pressure, you can start to have small earthquakes. But I don't think it's the physical propagation of the fault itself that's causing these problems. There's a lot of research going on, because basically, the nation is looking at this, and some of you might know more about this than I do, is there's a great opportunity there that we can supply the nation with, natural gas. It's cleaner, but part of the issue is what's going on with the water. There's big issues with the water. So the EPA is doing a huge study right now, actually, on it. And there's lots of different universities, especially in places, in the oil schools like Oklahoma and stuff, because they see this as a way to, really get their economies going again. Other questions? Uh-huh. 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 Yeah. Right. It's a very. What happened with the? Yeah, with the Fukushima nuclear plants, there were several of them, as you might know, and they were prepared for an earthquake that would knock out the electricity. They had these backup diesel generators that would keep the reactors cool. But when that tsunami came ripping through, it just took out the whole diesel system. So there was no backup to keep these reactors from, overheating, basically. But Japan's in this really difficult situation. It's a country that has basically no energy resources and this big industrial economy. So people have talked about bringing down coal from Alaska. There's a lot of coal in Alaska to, power what Japan wants to do. But you need to be near water, as you know, to keep a nuclear power plant cool. And so I think the country is really debating how to move forward, basically. And the prime minister of Japan said that they're under the most distress that they've been as a society since the end of World War II with this, because they have to decide how much money they're going to put into building these tsunami walls, how they're going to, power the country living in this dangerous area. And again, they thought, they thought they had this covered with the diesel backup. So, and then there's some people that are worried that there's this radioactive plume that's moving through the Pacific. It's going to end up on the West Coast at some time. So it's all these issues are related. Energy, earthquake disasters, all these. It's a good point. And Japan was like the model, right? It was the model of how to use nuclear energy in a safe way and to run a big industrial nation. And we still have a lot to learn. You can build it somewhere else, but you have to be. Yeah, exactly. But you do bring up a good point, sir, in that we have to solve these problems. These are international problems, right? So when you had the big earthquake in Taiwan, some of you might remember in 1999, they make most of the RAM, the memory for our computers, so the price is like triple because we're all related now, right? When Japan, that was like $28 billion is what they, in US dollars, of damage. Turkey, $25 billion US dollars. How do nations recover from this, okay? And we're all related. And so that's where we really need to get science back into things like the United Nations and these bigger scope things. We should have a, Earth scope program through all countries. Where are the active faults? Those kinds of things. Any other questions? Thanks a lot. I appreciate it. Hi, how you doing? Thanks for everything. I think it all worked well. Let me make sure I give you this before.